Hi everyone, welcome back to my channel. Today let's discuss about deep learning. Topic: Advancement in resource allocation, a survey of deep learning methods. Authors: Jeon Kim, affiliated by the Department of Electronics and Information Convergence in Engineering at Kyunghee University, South Korea. His research focuses on deep learning application in wireless networks, particularly in resource allocation and optimization. John Jung, also from the Department of Electronics and Information Convergences Energy Engineering at Kyunghee University, South Korea. He contributes to research on mechanic learning-based solution for wireless communication system and network resource management. In Holi, affiliated with the Social School of in Electronic and Electrical Engineering at Hankyong National University, South Korea. His research includes deep learning, wireless communication, and resource allocation techniques in complex network environment. Introduction to deep learning in resource allocation overview. Increasing complexity in wireless networking require efficient resource allocation scheme. Deep learning is being leveraged to reduce computational complexity and improve performances challenges. Traditional interpretive algorithms suffer from high complexity and inefficiency in large scale network. Deep learning techniques provide adaptive, scalable solution to these issues. Why deep learning is in resource allocation, motivation, complex data, wireless network generate massive amount of data, scalable deep learning models can handle complex high-dimensional data, optimizing learns optimal solution, reducing the need of high complexity computation applications, voice and image recognition, language processing, and resource allocation. Categories of deep learning based resource allocation. Supervised learning uses labeled data to predict optimal resource allocation. Example: power allocation in vehicular networking using back scatter. Reinforcement learning interacts with the environmental to learn optimal actions. Example: UAV based station deployment using deep Q networks, DQN. In unsupervised learning, no label data required, effective in dynamic system. Example: channel allocation to device network. Supervised learning in resource allocation, how it works, trains on labeled data to approximate optimal solutions, reduce the complexity of conventional algorithm. Example: power allocation in multi-carrier non-orthogonal multiple access NOMA system achieves similar performance to optimal solutions with lower complexity. Reinforcement learning in resource allocation, how it works, learn to take optimal actions based on environmental feedback can be applied to system with multiple devices. Objective example: energy efficiency, latency. Example: DQN based resource allocation in UAV assisted sensor network. Optimal energy efficient service for ground users. Unsupervised learning in resource allocation, uh, learns patterns from data without any labeled supervision. Ideal for time varying system where labeled data may not be available. Example: unsupervised learning for channel and power allocation to device D2D communication. Effective in handling dynamical changing wireless environment. Limitation of deep learning in resource allocation. Supervised learning requires large amount of labeled data which can be harder to generate. Reinforcement learning training by trial and error can insecure high consumption overhead. Unsupervised learning may not achieve optimal result compared to supervised approaches. Hybrid learning approaches. Hybrid models combining the strength of different learning methods to address imitation. Example, integrating supervised learning with reinforcement learning to leverage labeled data and adaptive decision making. Future direction explore combination of these learning types to optimal resource allocation schema. Challenges in practical implementation. Statistic network structure may deep learning models are designed with statistic structure, making them less adapted to dynamic work. Solution graph neural network GNNs are proposed to handle networks with variable input-output sizes, dynamically adjusting to different network environment, dealing with imperfect channel state information (CSI) problem. Wireless systems rarely have perfect channel state information due to estimation errors. Solution deep learning can mitigate performance degradation caused by imperfect CSI by learning to adapt to uncertain channel conditions. Future trends and research challenges. Emerging trends: heterogeneous learning, graph-based learning challenges. Conclusion summary: deep learning offers promising solutions for efficient resource allocation in wireless network. Supervised reinforcement and unsupervised learning each provide distinct benefits, and hybrid approach are the way forward. Future research further exploration of hybrid learning methods addressing real world deployment challenges like network dynamics and CSI estimation errors. Thank you.